All right, thank you for coming today. Hope your reInvent is going well. I'm excited to be here today to chat about some of the experience that AWS has had in building reliable, resilient systems at scale, and also to talk about some of the things that we've baked into the various serverless offerings so that you can get that reliability and resiliency kind of out of the box. And hopefully, by talking about how we do things kind of under the hood in Lambda as well, and you'll kind of see some techniques that you can borrow and build into your own systems. So resiliency is a very broad topic. It covers everything from deploying safely to, even just monitoring like your event management process, so that you can, if something does happen, you react quickly. But we're going to be focusing on the topic of overload a little bit more narrowly and just talking about many dimensions of this. So we'll get into things like load shedding. So if you get overloaded from traffic coming in, that you can drop that traffic really easily and handle it. There's protecting against overload from a dependency. If a dependency slows down, you don't want that to have a ripple effect up into your service as well. Queue backlogs are a really big problem because if there is a traffic spike, queue backlogs can build up and then just cause you to be continuously overloaded even if the traffic spike is gone. And then we'll talk about operations throughout, but we'll talk about especially the monitoring aspect of operating at the end. Because if you can't see what's going on in a system, you can't fix it. Throughout, we'll be kind of jumping around a little bit. Sometimes we'll talk about some theory, some computer science theory type stuff. Other times we'll talk about tools that are available in the serverless systems. And then we'll get into kind of why we built serverless the way we did and why we think that's a useful approach for you to simplify adding reliability to your systems. So first, since we're going to be spending the entire time talking about overload, we should probably talk about what that actually is. So when I think about distributed systems, I kind of draw inspiration from the real world, just kind of like an artist might. And so there's this quote from a poet. I didn't read it. I just saw it on the internet floating around and thought it was kind of applicable. But I think about this in terms of algorithms rather than art. I still think of it in terms of art. But for this talk, it's about algorithms. But I think the talk has it backwards, or I think the quote has it backwards in this case. I think that actually algorithms imitate life far more often than life imitates algorithms. Like you look in the real world, you see what's going on, you make a system do that thing. I don't think the real world models some computer system. But anyway, maybe it's a little philosophical. So one time when I was looking around me and my eyes were kind of opening to algorithms was between high school and college. I worked at a bank as a teller. I worked at a teller the summer before my first year and after my first year. And so I was starting to learn some kind of computer science algorithms, and I was a teller at a bank. So actually, I'm not sure if people really know what tellers are anymore. Has anybody actually in the last couple of years been into a bank and done a deposit or withdrawal from a human? Not an enormous number. Yeah, right? It's kind of a little bit of a lost art, but they're still around. They can always help you. So one thing, when I worked at the bank, you could come into the bank, or you could just drive to the bank and stay in your car at a drive-through. And you would actually put your transaction into this plastic canister and send it underground through pneumatic tubes, a series of tubes. That air would push your canister back and forth. And so you could send in your transaction, sit in your car, and then get it back and then drive away. So it's very convenient. And so there would be a bunch of people at the drive-through at once, each with their own kind of tube that they could send it through. So this meant, as a teller, I could multitask. I could work on multiple transactions at once. Because you can't do that when somebody's in front of you. When somebody's in front of you, you're not going to just say, oh, let me get the person behind you. Right, no, but with the drive-through, you could just kind of multitask. The problem is, when you're multitasking, sometimes you get a little bit bogged down in work. And then you start to slow down. Sure, your throughput might be good, but your latency can become worse. And there was this one time, there was a customer who said, you're taking too long, and I felt really bad. I was doing my best, but I just took on too much work, and they asked for their canister back, and they had to come back another time. So I was reflecting on this. I was like, what's going on here? And so what kind of models this kind of phenomenon is Amdahl's law, or the universal scalability law. And what these say is, it's actually somewhat intuitive. If you have work that you're trying to parallelize, well, you can do that by adding more, like I could have had more hands or something. But ultimately, there's some point of synchronization or contention, and that's going to be the theoretical maximum throughput that a system can have before it starts to slow down. And this is exactly what happens to server systems. On this graph, this is not time on the x-axis like you typically see. This is throughput. So it shows as you pile more and more throughput, you send more and more requests per second to a server, its latency stays pretty good. That's its minimum latency, its fastest response time from some period of time on that server at that throughput. But if you reach some inflection point, the server slows down very quickly, and it starts to get very slow very quickly. It reaches this inflection point where that point of contention kicks in. Making this even worse in a distributed system is that a client of a server will only wait for so long before it gives up. Like if you're rendering a web page, you as a customer is going to hit refresh after a while, right? Or just go do something else. There's a timeout. And if the server is slower than that timeout, well, you might as well have not taken that request. It's a failure. You didn't get useful work done. And the problem in this graph, the really big problem in this graph is when the fastest response time crosses that client timeout, that means every request the server is working on is essentially going to waste because the client isn't listening to the response. And so it's due at like 100% CPU utilization, all that stuff, but it's getting no useful work done because the client is never really waiting for the response. So that's a total brownout. That's when it's just the availability is at 0. Another way to look at this graph is to consider differentiating between goodput and throughput. So we still have throughput on the x-axis. You're adding more and more load to a system. That's offered load. On the y-axis, we're plotting goodput, which is the responses that were made in time where the client did not time out. So ideally, like in a perfect world with infinite resources and everything, this line would just continue to go up and to the right. As you offered load, you'd be able to handle that load and just keep chugging along. But at any point, at any instant in time, a server has only so much capacity. So it reaches this point, the inflection point, where it hits the maximum amount of throughput it can do. But then it gets slower and slower, and more requests start timing out, and then it gets down to a goodput or an availability of 0. So why does this happen? This is because servers are too optimistic. Just like me as a bank teller, I was trying to help everybody at once. And this optimism leads to waste. It's wasted work in the moment of being capacity constrained. That's the last moment when you want to waste work. You need to be perfect, or else you're actually just making matters worse by wasting work. Speaking of making matters worse, when clients time out, they start to retry. And so now let's say you're having a load-related event where you're handling too much throughput, clients are retrying. Well, what that does is accelerate you down that throughput curve. So if they start timing out, when getting a few timeouts, they're actually going to add work to the system, which causes you to time out more, which causes them to send more requests to the system, and then it just browns you out even faster. Now, of course, we do live in the cloud world where you should strive to never get into this scenario. We monitor our scale, headroom, all that stuff constantly. It's in many ways. And so you're scaling ahead of time. You're making sure you're not actually hitting this point in the curve where you start to get slow. But the reality is, at any instant in time, you only have so much capacity. And so that's why it's really important to understand where that line is so that you can be scaled, so that you know that you're scaled enough. So if you haven't done a load test like this, where you add more load and see where things tip over, you just you don't know whether or not your auto-scaling triggers are right. Your auto-scaling might be kicking in too late, and then you're actually slow. So it's important to test and make sure you have that headroom. But this talk is all about the inevitable scenario where you don't have enough headroom, where you're waiting for auto-scaling to kick in and save the day. Well, what do you do until then? So chapter 1 is about a technique called load shedding. Load shedding is very simple. It's just cheaply reject, well, it's simple to say. You cheaply reject the excess work. So the concept is this. If you look at that throughput and latency graph again, you take the stuff, the throughput that was causing you to slow down, and have the server cheaply reject that work instead of handling it. This assumes that you can cheaply reject, and that it's cheaper to reject than it is to serve the request. And so then your latency stays good. Now your availability still drops. Like if you look at the goodput graph, ideally it would have kept climbing forever, but you don't have finite resources. But at least it plateaus, and you maintain the goodput that you have the capacity for. And of course, at some point, you can only reject so many requests per second, so things do fall over. But that's a much better scenario. It's a better failure scenario. Instead of an availability of 0, you have availability of pretty good. or better. Now, another thing to think about around load shedding is to make sure not to waste work. We talked about all that wasted work and how an overload is the worst time to waste work. Well, what are some contributing factors to wasting work? Well, let's look at a sequence diagram. So here you have a client calling a server, time goes down. So when the client calls, it's going to wait some amount of time. That's the white line, and then it'll stop. That's the timeout. Now the client goes and does something else. Well, the server has no idea that the client timed out. That's just not part of the protocol, right? Like you don't send another message saying that it slowed down because anyway. So that's just generally not how things work. So the server has no idea, keeps going, even though the client doesn't care anymore, and it keeps wasting work. And you stack this in a distributed system with service-oriented architecture, you have layers and layers of this. You're wasting one server's time, it's calling another server, wasting its time, and so forth. So this is a problem. And so this is our first example of where a serverless kind of feature is pretty helpful and can improve your resiliency. And it's a simple one. When you configure a Lambda function, you tell it what function timeout to use. And so you can say, if you get your client timeout, if you kind of know what your client timeout is, your client's timeout, you can set the server to be somewhere around there. And then it will minimize the amount of work that's wasted. It'll stop working after it knows that the client must have given up. So minimize waste. It's a nice feature. And so this will push the good put curve out a little bit. You'll get a little bit better. This doesn't solve the problem completely, but that's why we're talking about multiple techniques and layers to all solve the problem. Now, you might be saying, well, the function timeout is something that's a problem, actually. You might be saying, actually, what if the client is going to send me a more expensive request? Now that timeout isn't suitable anymore. They might always hit the timeout, and they would never be able to achieve their request. And this is why, at Amazon, we find it so important to do bounded work in a given request. You've seen this. When you call DynamoDB, you're not asking for the entire 20 terabyte table all at once in one API call. You're asking for a little bit more, a little bit more, a little bit more. And so this is a technique that helps protect the server, because now it can tune these things like timeouts to know kind of how much work it's going to need to do in the worst case. But it also helps your clients, your customers, have more resiliency, because they can do some of the work and save their state. So to borrow from instead of the physical world, like in the teller scenario, you can borrow an example to think about from the virtual world, like a video game. So in a video game, you don't just go to the end of the game and then you're done. You save your spot every once in a while. In case you make a mistake, you can start over from where you saved instead of all the way at the back at the beginning of the game. Right, and then you can be successful the next time. And so this is important, and so we can make our systems do this too. So it's an important principle that we think about. It helps you set your function timeouts, and it helps your customers make their systems more reliable too. Now, another kind of cause for why servers become overloaded during an overload scenario is because they're too optimistic. So how can we sprinkle in some pessimism and make the servers take on less work? Well, let's look at it. So this is the same graph as we were looking at before. You have throughput increases, and the server's latency starts to sort of increase. Well, during that, there are some points of contention, back in Amdahl's law, the CPU. It starts to heat up. And now, when more request comes in, when more load comes in, there's actually less available CPU for each request than there was earlier. So at the beginning, there was a whole bunch of cores available for that, for those requests that were coming in. Now there's a little bit less, and now we're kind of really trying to fit everything in, and there's just less available headroom for every request, and that's why things slow down. Eventually it gets bad. Now there's kind of an interesting shift when you're on serverless on Lambda. In Lambda, your function, when it's executing, has its very own execution environment. Sometimes we call it a sandbox, sometimes we call it a container, sometimes we call it an execution environment. And an execution environment has fixed resources that you configure. You say, I want this much memory available for each function invocation, for example. And now, each request, while the request is running, gets its own execution environment. You don't have one execution environment working on multiple things at once. We'll see why that's so important. If a new request comes in, we'll spin up a new execution environment. If one finishes, another in that execution environment, if we haven't spun it down, is available for another request, and this sort of thing. Now, this is such an exciting simplification. I think in Lambda, like one of the things that I talk about with customers so much is all the kind of developer agility you get, the elasticity, the cost savings by not having to do peak planning. But this is one of the more exciting things, in my opinion, and here's why. That latency versus throughput curve, every request that comes in has the same amount of resources as every other request. If you add more load, you just add more parallelization. They all have the full resources of that sandbox, that execution environment. The thing that we were talking about, that curve of doom, just doesn't happen in this way for the Lambda functions. So at least it's complicated. You could have the database that tips over. You could have something else happen. But at least this thing just makes your whole system more easier to reason about. So we talked about just simply adding some pessimism to your systems, to our systems, so that they don't take on too much work. We talked about simple things like just rejecting load when you know you're overloaded. Just don't accept more work. Don't waste work. Don't just continue running forever, even if your client has timed out. Doing bounded work is good for you, and it's good for your customers. And then we talked about just the inherent properties of Lambda. One of the more exciting things to me in Lambda is that you just have this resource isolation, not just between servers, but between requests, between units of work. All right, so now let's talk about what happens if a dependency gets slow and could potentially cause your service impact. And so this chapter is all about this concept of concurrency and running out of it. So one thing we talked about before that we were running out of were physical resources, like the amount of CPU, the memory. But there are also other things that you can run out of as an application. You can have a thread pool configuration, software limits, soft limits, like thread pool size, number of file descriptors that are available, number of ephemeral ports. All these things can happen, and these are the things that influence the concurrency bottlenecks in your system. You might say, oh, I'm not a thread per request, I'm all this non-blocking, but there's still other resources that you're going to run out of. So concurrency looks like this. You have a client talking to a server. At some points in time, in this case, if there's just one client and one server, the concurrency is 1 while that request is happening for the duration of the request, or it's 0 when there isn't any request going on. Now, the concurrency can increase for 2 reasons. The first reason is if the arrival rate increases. If the arrival rate increases, the concurrency goes up proportionally. Similarly, if the arrival rate of requests had stayed the same, and the latency on the server to process each request went up, well, then the concurrency also goes up proportionally. And so the theory behind this is called Little's law. Little's law says that the concurrency in the system, on average, is equal to the average arrival rate of new requests times the latency, on average, of each request. So to picture this, I'm a visual person, I look at the real world. In the bank, the number of customers in a bank, you can kind of predict it. If you were like, how many customers are going to be in the bank at 5 p.m.? Well, it would be, I know what their arrival rate will be, so I can multiply that by how long it takes me to process each transaction. And that is the number of customers that would be in the bank at 5 p.m., probably, average. OK, so now, another kind of real-world thing to draw on, this is about concurrency and dependencies, is in the bank there are 2 types of transactions that I would help customers with. Check transaction, which is very fast. It's just easy. I just punch in some numbers and go for it. Or a cash transaction, which also can be fast if it's a small transaction. But if it's a large cash transaction, I would have to wait for my supervisor to go to the bank, to the vault. Because it takes a little while to go to the vault. You have to fill out paperwork to make sure you're doing the right thing. That's an important audit checkpoint. And so this system, this like distributed human system, is sort of like a distributed computer system. You have the customer, who's the client. You have the service, which is the teller. The vault is sort of like a database that you have to go to occasionally to kind of get more information. And then like this drawer that I have in front of me for like small amounts of money is the cash drawer. OK, yes, I worked on that. Thank you. OK, so great. So we have this cache database. Now, what's the problem is, in this case, I can only work on one thing at a time. And so if somebody comes in with a large cache transaction, cache miss, I suppose, so that they expect that large transaction is going to take some time. It kind of feels good for it to take a long time. Because like, ooh, this is a lot of money. Right? So they expect it to take a while. Now, the poor people behind them with transactions that they expected to be, oh, this is a quick run to the bank, I just deposit this check and go. They're going to be upset because they're having to wait behind the large cash transaction. So how do we solve this problem? This distributed systems problem can happen in servers too. How did we solve it in the real world? Well, you can just have multiple lines with dedicated resources. So we can have somebody who's saying, OK, I'm going to work on the quick transactions, and if there's a large transaction coming in, they'll be in this other line. So you can do that. I mean, there are a bunch of variations on this. I'm sure you're imagining a bunch of other ways to solve this problem. So now to talk about how to build this into computer systems, distributed systems, let's talk about under the hood in Lambda about how we solve this in one particular place. It's cool to kind of draw in an example. So this is the Lambda architecture for the invoke path. It's the current Lambda architecture. We change it, so like don't make too many assumptions about what's going on. It's also a simplified architecture. Don't need to get into all of it right now. But there it's made up of microservices. You're the user. You're eventually going to call the invoke API to say, hey, run my code, here's the input, and I'll wait for the response. You're making a request to the front end. The front-end web service, there's a load balancer. I'm not picturing all that stuff. But it authenticates your request to make sure you're allowed to do the thing you're trying to do, validates it, all that stuff. Make sure you're performing bounded work, these types of things. Front-end, though, doesn't know what kind of it is stateless. It doesn't know anything about what servers are available to run your function. So it asks the worker manager. That's its job, to keep track of this stuff. Worker manager, though, in this case, it doesn't know about any sandboxes that are already running for your function, because maybe you haven't called it in a while. So it goes and asks placement. Say, hey, placement, you know about kind of the worker fleet. Why don't you just kind of figure out a place that I should kind of be tracking to run a sandbox? So placement will find the suitable place and run it, get a sandbox running. Worker manager will talk to it and say, hey, download the customer's code, start up the VM, all that stuff. Get it running, and then tell the front end, OK, it's ready to go. Send it the payload. It's going to invoke the customer's code. So that's a cold invoke. That's when we didn't have a sandbox running. That's one mode of operating that we're going to talk about. That's sort of the cache transaction. You have to go to the vault. Now there's a warm invoke path, which is different. Same kind of stage. The front end gets the request. It asks worker manager, where should I put this? Worker manager says, aha, I know where there is an idle sandbox that's already ready to go for that function. So it'll say, OK, heads up, sandbox, we call them. There's an invoke coming, and it says, OK, and then the front end sends your payload there. So that's a much faster interaction. And so remember, this story is about concurrency, so let's look at the concurrency on worker manager from these same API, two modes of operating. Well, the front end, if it calls worker manager for a warm invoke, that's a short thing. It doesn't use very much concurrency for very long on the worker manager. But when the front end calls worker manager and it's a cold invoke, it needs to ties up more resources on the worker manager for longer. Not a lot of resources, but there is, again, we talked about those software limits that exist. And so, concurrency, if there's a high request rate of warm invokes, the concurrency is still slow. It's still small. It's low concurrency. But if it's a high request rate of cold invokes, the concurrency is higher. And that's this other kind of mode that we have to be careful about in Lambda. And so we'll talk about some of the ways in which we're careful about it. Well, there are some limits, software limits in any system. So let's just say for this picture that the concurrency limit is 4. The worker manager can handle 4 concurrent requests. So if some warm invokes come in, they kind of fit depending on when they come in. There's some room for them. But if warm invokes come in and the worker manager is already tied up working on these cold invokes, that's a shame. Like we would have to retry those requests on a different worker manager. And it's a shame because they were warm, meaning that worker manager knew about some sandboxes that were available that we could have quickly executed that customer's function on. And so we really want to make it so these warm invokes happen. Whenever an invoke comes in, we want to make sure if we have a sandbox, we use it. We kind of think about the goals of this system, of this particular microservice. Automatically scale, spread out work, like we'll retry work across worker managers. We'll spread out your workload. Not getting into that right now. But the key requirement, or tenet or something, is that we favor reusing. If there is a sandbox available for your function, we really want to use that because it's going to be faster for you and it's better utilization of the fleet. And so what this ultimately comes down to is that warm starts are somewhat more important locally to a given worker manager at an instant in time. They're kind of more important because they could enlist the help of another worker manager for a cold start, but warm starts only it can handle for that if it has an available sandbox. And so, just like in the bank, how we had 2 lines, one for the fast, one for the slow, that had some things in terms of the utilization of us as tellers, like we wouldn't always be, somebody might be idle, but just sitting around just in case a warm transaction came in. We can do that same pattern here for worker manager. So we'll split the concurrency into 2, for warm invokes and cold invokes. So when warm invokes come in, they use the warm invoke resources. And when cold invokes are in, we decide, OK, we'll use the other the more limited cold invoke resources and just artificially limit the amount of resources that we'll use for them. So if a cold invoke comes in, that means we didn't have a sandbox for that function right then. We have to make a new one anyway. We'll just make it somewhere else. We'll give another worker manager take care of it. But if a warm invoke comes in, this is the worker manager that has the capacity. It has to be the one to answer. We're prioritizing it. So we've kind of made it so that we have dedicated resources just for those more important warm invokes. So that's about it. It's a pretty simple approach. It's implementable with like a semaphore, atomic integer, separate thread pools, something like that. But why, so we do this because we want to take APIs that are unrelated and make sure that they don't share fate with each other. That if one has a problem, the other doesn't, or a spike, the other doesn't know about it. Also, we protect, with what we were talking about in the worker manager's case, we protect against modal behavior. It's one API, it just has 2 modes of operating, which is kind of a red flag. It's something you should think about whether or not you can avoid that multi-mode operation, like when you're using a cache. Using a cache, a quick aside, using a cache is great. It improves your latency, can improve your efficiency, but it has this mode that your workload can flip into when you start not being able to use the cache, maybe because of a software change or a workload change. It flips into these 2 modes, and so you should isolate that dependency of your database from your cache so that you can keep operating if one of those modes is affected. And so how? OK, finally getting back to some more kind of practical advice about how to do these things on serverless. Well, there are a couple of different ways. If you're using API Gateway for fronting your APIs, you can set a throttle on each API to say, OK, this API is my bread and butter. I'm going to give it a higher throttle limit than this other API, which is intended to be called less often. You can even set different throttle limits per one of your customers. We'll talk about that a little bit. Also, in Lambda, we were kind of talking about concurrency. Well, you can also control your concurrency between 2 functions and set a limit on one function to only use so much of your concurrency and yet let other ones have more. And so in practice, if you have this cache in the database, your Lambda function might just check the cache to see if it's there, but it wants to be protected from if the database gets slow, which would drive up its concurrency. So it could call an API gateway, which talks to the database. And the API gateway could do rate-based throttling because it knows the database can only handle so many queries per second before it slows down. Or you could have a Lambda call another Lambda function and use per function concurrency control on the one that actually talks to the database. These are just options. There are a lot of ways to do it, but just kind of wanted to show that there are these features in serverless, but they're composable like this. OK, so that's dependency isolation to prevent you from becoming overloaded when a dependency slows down. But what about this other topic, which is avoiding queue backlogs? Queue backlogs can be a really big problem where you take a load event and then you can extend that duration of that load event long into the future. And so we really want to be careful about that. So let's go back to the bank. So in the bank, people would show up. The traffic would come in, would vary from different parts of the day. Like at the end of the day, when people got off work, there'd be a little bit of a rush where people would come in and want to do some withdrawals or deposits. But then, at the very end of the day, when stores started to close for the day, their kind of business owners would come in with a whole bag of transactions, like their whole day's worth of checks or cash or whatever, that they would have to come in. And that would take us a while to work through that entire bag of transactions from each of those business owners. And they would show up. There was a correlated workload. These workloads were correlated because they were time correlated. They would show up at the same time. So that was a problem. Now, just like the cache and the check transaction isolation, the business owners understood that these were going to take us a while, and they understood that there were other customers who had urgency who wanted to be dealt with quickly. So the business owners would leave those bags of transactions for us to process later, kind of as if we had a lull or later on after we closed. And this is great. This was very customer obsessed. We were able to make everybody happy, right? The business owners were happy, and the other customers were happy. The problem is, we were happy that they were happy, but we were less happy because we had to stay a long time to deal with this backlog that would build up. And so that's less great. So to look at ways that we can fix this in serverless, let's actually look to sort of a sample application. This is an application that you can find on GitHub. I'm going to really paraphrase its architecture a little bit here, just for the sake of the talk. But let's say this is a chat application where you have Alice kind of and Bob, or like you have a chat room, and like people can be in the chat room, and you can send messages and receive messages to whoever says stuff. So let's say they're both connected in their phone to like an API gateway over a WebSocket. So that's a long-running connection where you can receive messages. It's bidirectional. So Alice could send a message saying hi to the chat room. The API gateway could take that request, and we could put that into a queue. Because maybe if a message gets if there's some problem processing it, we want to make sure that we reliably deliver that message. So it could be in a queue so that we can retry. Chat service could pull it up. That's like Lambda using SQS as an event source. Chat service would say, OK, first we want to maintain chat history. We'll store that in DynamoDB. And then we need to look up and say, hey, who all is in this chat room? I need to send them a copy of the message. And then the Lambda function can send a copy to each of those recipients by calling API gateway. So that's about it. You can find this on GitHub. Now, let's look at the queue, because this is all about queuing. Well, in the typical case, the messaging application will be very quick. This is using systems that are all quick, that scale, that are all kind of suitable, and so for this use case of near real-time communication. And so typically, the queue is empty, and the resources are not super utilized. But what happens if somebody gets really excited and starts sending a whole lot of messages? Well, that can, Lambda will scale quickly, actually, very rapidly, just spin up more sandboxes to parallelize your workload. But the queue will fill up, and you have some limit, some function concurrency limit set of how much concurrency you want this chat application to have. And so the queue will start to fill up because you aren't processing messages as fast as they're arriving. OK, fine, though. Like, the traffic spikes happen. We've been talking about that the rest of the talk. But what's different here? Well, when the traffic spikes goes down, you're still down. The system is still down because it could have built up such a backlog. Just like me as a teller from all these businesses coming in, I build up a backlog that's going to take me a while to drain. And I'm still overloaded the entire time as I work through that backlog. That's a bad thing. So what's a more ideal customer experience? Let's figure out how to solve this problem. Kind of like you have this durability versus like resiliency trade-off here that we're making that's kind of hard to make. Well, we know what the unideal experience is. Like, you think of what the customer impact would be of this. Alice might be setting up a meeting with a bunch of people, so they've sent a message to agree on a time that they're going to meet. But then Alice right before says, ooh, we need to cancel this meeting. But if the queue is overloaded right then, Alice doesn't know that Bob didn't get the message. Bob didn't get the message. Bob shows up and wonders where everybody is. This is a classic Byzantine generals problem of two generals trying to coordinate an attack when they don't know if their message to agree to the attack has been dropped or delayed or redelivered. So it's a classic problem in distributed systems. So the contributing factor to make this a problem is that queue backlogs for systems like this are pretty bad. One of the reasons that's making those queue backlogs so bad is because we tend to use queues that are FIFO-ish, first in, first out. When you put a message in, the producer of the messages puts the messages in at one end of the queue, and the consumer is always pulling out the oldest message. That's just the contract of the queue or the behavior of the queue. And so that means the consumer, when there's a backlog, all of the messages are slowed down, every single one. In contrast, a last in, first out queue, the producer and consumer are both working on the same end of the queue. So if there is a load spike that subsides, the messages that are delayed are the ones that showed up during that overload time. And so after the overload, the consumer would go back to processing the freshest requests. So that's kind of actually a nice property of LIFO, what we might want here. So how can we take some service like SQS, which generally gives you a FIFO-ish behavior, and make it behave a little bit differently? Like SQS is a great service. It gives you all the scale, performance, elasticity, but we kind of might want to make it behave LIFO-ish in some situations. Well, you actually don't need a different service for it. You just use SQS, just use it more. You have two queues, a high priority queue and a low priority queue. And so when your service is deciding what to work on, it first checks the high priority queue, gets a few messages. If there's nothing there, we didn't get any messages right now, well, then check the low priority queue. And if there are only if you didn't see anything in the high priority queue. Great. Doesn't work. Not for this situation we're talking about. Not quite. So the problem is, in this chat service, all of the messages are high priority. When they come in, they're all fresh. We want to work on those. So they're all going to go there. So when the chat service gets a load spike, it's just going to put them all into the high priority queue. But all is not lost. We can add some logic to the chat service to say, well, OK, let's say messages get old. That surge kind of happened some time ago. Now all the messages turn green, which means they're old. Well, in the chat service, more messages come in. But when the chat service gets a request or gets something from the queue, it can say, oh, this message is old. It's just a simple logic. This message was in queued a while ago. Let's just cheaply put it into the low priority queue. It's cheap to just put, this presumes that it's cheaper to put a message into a different queue than it is to actually process it. So let's assume that's the case. It likely is. So you keep receiving messages. Occasionally the chat service will see a fresh message and it'll process it right away. That's great. And eventually, after this backlog happens, it'll eventually move all the old messages into the low priority queue. And now it's back to working on the high priority queues, and all those fresh messages are preserved. They're happening right away. And then you still have that durability property of being able to get through the low priority queue when you have time. So you didn't drop messages. You just delayed the ones that occurred at some point in time. But when that surge goes away, you immediately kind of went back to processing the fresh messages and appearing available, even though you had some work that you have to go back and do. Now, I mentioned this idea of dropping a message. Maybe you should think about in some systems, like I worked on the AWS IoT team for a while. And one thing we saw that a lot of IoT devices would be built in a way where they would just check in and re-report their full state every once in a while. Now, you might want to capture the historical state to be able to do some machine learning stuff and make your whole system smarter. That's sort of one of the big points of IoT. But if you are faced with a backlog, you might say, well, I know each of the devices are just going to come back in 5 minutes anyway. So if I'm working on something that's more than 5 minutes old, I'll just drop it because I just know the device is going to re-report. This isn't something the IoT core does. This is something that you could do if you had a use case like this. Now, again, back to like kind of practical advice that you can just use on serverless, just like a knob that you can turn. You don't have to implement code. If you're invoking Lambda in an asynchronous way, where you can say, hey, Lambda, invoke this function at some point. I'm not going to wait around for the response. And retry it if it fails, if my function fails. That's an asynchronous invocation on Lambda. So if you have that, as of last week, we've actually now given you a knob that you can turn to say, if messages are older than some configured amount of time, or if Lambda has attempted to call your function enough times, do something else with it. Don't keep trying. Just put it into a dead letter queue, drop the message altogether. It's a feature, just a knob that now Lambda will take care of for you, this like movement of messages so that you can get back to working on fresh messages. So you don't even have to add code for this. It's pretty convenient. So that's one way to deal with queue backlogs. Another way to deal with queue backlogs we sort of talked about before. Just don't have a queue backlog. It's easier said than done, but actually with API Gateway, it's a tool that helps you have that property. You can set a throttle limit to say, OK, I know how much capacity I have in my Lambda function. I know how much concurrency I have. I know how much DynamoDB capacity I have. You could set an API Gateway throttle rule to only allow that much traffic in. And if more traffic comes in, that load spike happens that we were talking about, where somebody got excited and sent a lot of messages, well, that would be rejected by API Gateway. But that's actually, this sounds like, that's not very customer focused. Customers are going to see errors. Well, they were seeing a bad customer experience anyway. This is sort of like an inevitable, like an unavoidable situation. So at least this way, Alice knows that the message didn't get to Bob. And Alice could go and text Bob instead to say that the meeting was canceled. So this is like actually possibly even a more helpful customer experience, is to give that feedback. Now, another way that you can do this, actually more throttling techniques, and I'm going to talk about like limiting the throttling to the workload that's driving the overload and not just spreading it to all customers. But it's like API Gateway has a bunch of throttling capabilities. But another kind of borrowing that same throttling technique, let's say, oh, I don't want to reject messages because it's more important to have the durability than the feedback. Well, one thing you could do is you could say, well, OK, I'm going to do throttling where I'll let so many requests in per second to the warm queue. But if I'm handling more requests per second than that, I'll take those excess messages and put them directly into a surge queue. This is sort of the same thing as what we were moving messages from the warm queue to the surge queue, but you can get them to go directly into the surge queue this way. You have to implement the throttling logic yourself, though, in this case. And then you can have separate Lambda per function concurrency there so that the surge queue is handled by dedicated resources that aren't going to crowd out your other function that's responsible for the warm queue. All right. So there's one other kind of way of doing queuing, protecting a queue-based system that I want to talk about, and that's called Shuffle-sharding. This is actually a technique that isn't usable only by queuing systems. We use it all over the place at Amazon, in Route 53, in Hyperplane, which is part of our virtual network. Route 53 is a DNS system. We use this technique all over the place, but it works well in queuing as well. And we use this in Lambda, under the hood, for our queues. And this is, again, in the asynchronous invocation path we talked about, where a customer is going to invoke a function and not wait for the response. They're expecting us to redrive the function until it succeeds. So if you're calling this asynchronous invoke API, you're calling that API. It goes, this time I pictured the load balancer. So it goes through a load balancer and arrives at that same front-end service as we were talking about before. So the front-end service, it enqueues the message into an SQS queue that Lambda operates behind the scenes. You don't see this, but it's an SQS queue. It's more complicated than that, but we'll get into it. So it puts it into a queue, and then it responds OK to the caller. It says, OK, yep, we have that message. It's durable. It's an SQS. Now, a separate microservice called the poller fleet goes and is always polling that queue and receiving messages. And when it receives a message, it doesn't do magic. It just goes back to the front end and calls the synchronous invoke API on your behalf. And that's simple. And it does all the redrives that need to happen to make sure that your function completes or puts it into the DL queue like we talked about. And then it deletes the message once it's done one of those two things. So this part of the talk is all about that queue and the poller and the front end. So let's zoom in on those and then look at the queue and all the customers. So let's say each of these shapes here, these customers with a shape, is every one of you. You're all of Lambda's customers. And there are a lot more than you. They're everywhere. Great. So if we were to, we don't do this, but if we were to have one queue for everybody, what would happen? Well, that queue would occasionally have messages from everybody in it. But what if one of you got really excited? You're load testing your system, which you definitely want to do. You want to run load tests to make sure you understand how your system behaves. That's a key part of resiliency. Well, you would fill up that queue, and that would kind of crowd everybody out, which would be a poor experience. So we don't do this. What else could we do? Well, we could have a separate SQS queue for every one of you. And that would be a lot. Then that way, if one of you got really excited and did a load test and sent a bunch of messages, it would only backlog your own workload, potentially. But it wouldn't do a backlog somebody else's. Why don't we do this? Because the polling, there are a lot of you. That would be a lot of queues and a lot of pull requests to SQS. It would not be efficient. We could do it. It just wouldn't be super efficient. So what do? We get the best of both worlds through magic of shuffle-sharding. It's magic just because I'm not really good at math. I will show you some math, but it's pretty magical to me. So instead of creating one queue for every one of you, we create n queues, some fixed number of queues. And then we map each one of your workloads to two of those queues at random. So let's look and see what happens when we do this. So there might be some messages from one customer in some of their two queues, the two queues that they're mapped to. But now if somebody else, like this lightning bolt shape, comes and does an invoke, the front-end service will actually first check to see which of the two queues for that lightning bolt customer are emptier. And so it picks the emptier one and then queues the message into that queue. Now, well, what happens if star customer, again, gets really excited and drives a backlog? Well, there are some other customers who overlapped with them. So that's not good. But actually, what happens is, again, if one of those customers that overlaps sends a message, we find the emptier of those two queues first and automatically route around the backlog. It's just magical. It just magically routes around it. So that's part of the magic. Now, the other part of the magic is just how these numbers work out. It deals in factorials. So it doesn't take a very large number to result in quite a bit of resource isolation. Let's say one customer becomes very busy, like the star customer. Well, if that customer gets very busy, what is the probability of another customer being affected by that? Well, there's actually a 53% chance that your workload doesn't overlap at all with that one customer. Just from assume you have 8 queues and you map everybody to 2. So there's a 53% chance that you don't overlap at all with that customer or that other workload. There's a 42% chance that you have one of your queues overlapping, but we'll route around that, like I described, by checking and going to the shorter of the queues. But now there still is a 3.6% chance that you completely overlap. And that's not good. That's actually a pretty high probability in our mind. We don't want that. Now the magic is here. What happens if you have still a modest small number of queues, 100 queues, but now you map every customer to 5 randomly? Well, now there's this tiny chance that you fully overlap with that one hot workload. It's just so small. It's amazing how quickly those numbers get small with just going from 8 queues to 100 and from mapping to 2 to 5. It's pretty magical. Now, still, even despite the magic, if there is a hot workload, we eventually detect it and create a different queue just for that workload, just for good measure. So that's it. Shuffle sharding is pretty magical. But queue backlogs, we pay attention to very closely to make sure to avoid them. And so we talked about a bunch of techniques around queuing. I just want to recap, because we went kind of wide and talked about a bunch of techniques. So first of all, queues, if you have a queue in your system, be very paranoid, be extra paranoid and pessimistic about that queue. Think, OK, well, what happens if it were to get really backlogged? What if I were to go down for a while and then came back up and had a backlog? What if the arrival rate went up and I had a backlog? It's actually the same concurrency. It's Little's law again. There are 2 things that affect your concurrency or your queue backlog size. Little's law, once again, arrival rate and latency. So definitely scale. You want to scale out of a queue backlog. That's definitely just like, it goes without saying. Just add more hosts if you have a backlog. Add more capacity from Lambda. We talked about how you can actually kind of just route around this problem by having a high priority queue and a low priority queue to move the backlog into a low priority queue so you'll get that backlog later. Sometimes you might not even really care about the messages in the queue as much, and you might want to just drop them to make room for because you know that the clients are going to behave in a way that will be acceptable. You can also apply back pressure to prevent the queue backlog from growing. And with the throttling features, you can operationally react and change the throttle limits on the fly as long as you have that in place to begin with. And then you can, we talked about another kind of throttling kind of derivative where you can actually use throttling to route messages into a surge, excess traffic into a surge queue. And finally, we went under the hood in Lambda a little bit and talked about surge queuing. And it's a technique you can do as well, on Lambda, on serverless, or otherwise. So now let's talk about operating a little bit. We've been talking about operating, but let's talk about the metric side of operating. The reason why I find this so important and spend so much of my own time focusing on this is because you can't actually, if you can't detect and react to a problem quickly, then your system isn't actually resilient and reliable. Like, things are inevitable, and you need to be able to see when they happen and address them as quickly as possible. And so having operational visibility at your fingertips of all of your operators and being trained to know how to deal with things is actually incredibly important in practice. So there are a bunch of tools that you can use. Maybe you know about some of these, and I'll just kind of explain why I care about these tools so much. So there's a tool called X-Ray, which lets you trace your requests through your entire system. So when your requests come in from your customers to the entry point in your system, you can enable X-ray tracing in that and then every other hop in your system so that they pass this kind of baton, this trace ID, which links all of those units of work so that you know what the different systems are that are collaborating on that given unit of work. And so from this, because you've plumbed this kind of trace ID through your system, X-ray can now build this map. This is a map that's made in pretty much near real time that shows all of your components. I put this, it's hard to read the text, but I put this in place for that chat application that I was talking about earlier. So this shows the login function when customers log into the chat room. It shows the send message function when you're sending a message to somebody else. It shows DynamoDB and the latency and error rate to all of these components. So it tracks for each component the latency, the error rate, the request volume, the throttle count, all those types of things. And so here you can see at this point in time when I took the snapshot, I was having the yellow in the upper left meant I was having some kind of latency issue with my login function. Kind of drove some load at it to make that happen. So you get this map of all your systems interacting, and when something heats up or something has a problem with it, you just look at this map and it'll be red. The circle will be red. It's just this really great entry point to diagnose where the problem might be in your system. Now, it's actually even more useful of a tool than that. It's still pretty useful. But what you can do is look at a specific request in your system and say, OK, well, this request was slow for some reason. Let's figure out why. Or it failed. Let's figure out why. So because you've been passing this baton around, X-ray will keep track of the latency and every interaction in the system, how long each interaction took, and plot it for you on this kind of chart. Now, quick aside as to why this excites me so much and why this is so important to me is because I looked at this when I made this slide a few months ago, 6 months ago, and I was like, well, this is weird. This is not right. I used to work on DynamoDB, but I can see that the DynamoDB latency is 80 milliseconds, and that's not the DynamoDB latency. It's single-digit millisecond, not 80 milliseconds. And it was consistent. It was like this wasn't an outlier. It was happening every time. I'm like, this is frustrating. What happened here? And so I dug in. I didn't even know that this was a problem. Didn't realize it. It wasn't until I just looked at this picture. And what the problem was, I realized, it was a configuration problem in my code when I was not using persistent connections in the SDK. So when you make a request to a service, you have to first do it through a TCP handshake and TLS handshake and all this stuff in order to be able to have a connection open that's secure in order to make a request and get a response. Well, typically, that's slow. That actually turns out about 75 milliseconds in this case. Because every request to my Lambda function, I was having to reopen that connection and just throwing away the old one. And that was wasteful. What you typically do is amortize that 75 millisecond handshake and you reuse it for multiple requests after that. So your typical latency would be very low. And so I just found this configuration problem and fixed it. So it was only because I was looking at the operational data that I noticed this problem. It's sort of an aside. It's not as much about kind of availability. It's more about performance. But still, it's just this tool is so useful. I can't stop talking about it. Another thing I do a lot of is I look at logs. And I look at logs not just from one server or Lambda invocation or something like that. Sometimes you need to answer questions across all of your logs to look for a pattern. So let's say, for example, you have some operational event where you have more load than you're expecting. Where did that come from? Who's sending it? Why? And so you need to be able to look at logs to figure that out. And so Amazon CloudWatch Insights, I think this launched last year, was one of my favorite launches. It was my favorite launch that entire year. Because it's now this tool that you can use without having to run any kind of MapReduce cluster or anything. You can issue aggregate queries across all of your logs, and it scales phenomenally and it operates on very fresh CloudWatch logs data. So if you have data in CloudWatch logs, it will do parallel analysis based on whatever aggregate query you write. Here's a query that I wrote, again, while I was doing this chat demo. I was trying to figure out what my peak per second concurrency was of my Lambda function. Because Lambda, we emit concurrency metrics. We emit all these metrics for you to CloudWatch. But those show minute statistics. I wanted to see per second. Because often you'll find interesting behavior if you look at per second instead of per minute or per hour or per 5 minutes. Now, actually, as of last week, Lambda now supports percentile metrics for concurrency. So now you can actually plot not just maximum, average, minimum concurrency. You can also plot percentile metrics like what is the 90th percentile or something. But anyway, my point here is that CloudWatch Insights is an important operational tool to be able to analyze what's going on en masse across all of your workloads, to find a workload or find some problem. You're trying to find the needle in the haystack. Well, you need to be able to query across your logs quickly. And so I always have, now I'm not always writing these queries on the fly. Whenever I find a query that I find helpful to deal with an operational event, our teams will make sure to write that down. Be like, we have this recipe book of all of these queries that we find to be important in different situations. And share those between your whole team so that you know when you're operating your service how to find answers quickly. Super important. Now, another really important operational thing that we use, tool, is CloudWatch metrics and dashboards. This is maybe the kind of starting point. They're all important. I'm going to say the most important for every single one of these. But if you, maybe it's kind of the starting point when I'm looking, when I'm on call. We have a dashboard for every component, sometimes multiple dashboards for every component. If you have a system that uses some service that is emitting metrics, like if you have an application load balancer, it's emitting a lot of useful metrics like request volume, error rate, latency. If you have DynamoDB, it's emitting your provision throughput, your consumed throughput, your throttles, your client errors. It's emitting all these things. And if you don't have a dashboard that shows these things, that are important for your system, then what are you going to do? If you have an operational event, are you just going to go fish around for metrics? No. If there's a problem with the system, you want to see all of the metrics related to that system. Now, you're not just going to put them in random order. All of our dashboards kind of follow the same pattern. We have and you think of it in terms of kind of the customer. So we have the request volume, that's kind of how much traffic customers are sending us, as measured by whatever the front door to your system, like the application load balancer, your API gateway, whatever. And then after that, maybe that calls a Lambda function, so you have all the Lambda latency metrics and the errors and all that stuff. And that might call DynamoDB, a cache, whatever. You see how this just kind of goes down as your dependency tree for a particular component. But then you also need to break it down to say we have different APIs. Each API has different, you don't just look at overall latency, you look at per API latency, all these things. Now, actually, one other thing that the CloudWatch folks launched just recently, maybe this week, I talked about how we start at the top, as close to the customer as we can get. Well, we actually go even further, and not just at our entry point. We actually go further. We always have synthetic workloads that are being driven, that are customers. We have our own kind of customer workload exercising every API we have regularly, every kind of use case, so that we can see from your perspective with our own system, our own canary or synthetic workload system, how we're behaving. And so now CloudWatch, you could always do this. You could have a Lambda function. You could have anything. But CloudWatch Synthetics is a new service that will help you just make it easier to write these canaries, these synthetic workloads that are constantly testing your service. And so we'll do things, these metrics, these client-side metrics are so important because you need to be able to see what you're not seeing in the service side. And then you can also automatically roll back deployments if you see any problem in the canary workload. You can actually, depending on how you architect your service, you can deploy such that the canary is the only thing that sees your new code first before you deploy it to the rest of your fleet. Kind of dropping these little things that are just neat little tips, I guess. Now, I mentioned that we need to be able to find a change in a workload very quickly. If we see a request spike, we don't know necessarily just by looking at our volume metric who that's from. And I kind of mentioned, well, we would use CloudWatch Insights to dig into the logs to figure out count the number of requests grouped by the account ID or something. Well, now also this week, the CloudWatch team announced a new feature called CloudWatch Contributor Insights. So this, you can just configure your logs to say, OK, here's in my CloudWatch log where I'm logging the customer ID, some kind of parameter related to a different workload, the resource ID, something like that in your service. And then you just configure Contributor Insights. This took me about 15 minutes or something. That's just because I didn't really know what I was doing yet. And I just took that same chat example and told a contributor insights rule where to find the user who's sending the messages. And then I kind of drove a synthetic workload to make it so that the messages were coming from me. And so then you can see, like, sure enough, if you can see it just visualized without having to run any queries and logs where the workload's coming from. Lastly, CloudWatch announced Service Lens, which is it just ties together all these different like logs and metrics and X-ray to make it easier to jump between them. So let's do a quick recap. We covered a lot of things. We talked about load shedding and making sure that you don't take on too much work, because if you do, your servers are too optimistic and they'll just start keel over and have a zero availability. And so you can reject the excess work. You can use something like Lambda to make sure that you have isolation between every single request. You can make things better for your customers by doing bounded work so that they can checkpoint. You can compartmentalize dependencies so that if a dependency becomes slow, it's isolated from others and your system keeps working, doing the other thing. You can use API Gateway and Lambda for that. You can do a bunch of things to keep queue backlogs from happening. We went into that in great detail. But so I hope at the kind of end of this, you kind of see that there are all these patterns that you can do in serverless that makes your systems just inherently more resilient. So you can please do the feedback thing. It's really helpful to help improve these talks. And you can also, I didn't put this in the slide, but you can look up my name and follow me on Twitter and see what we're talking about here. Ask me questions there. We'll take questions outside. Thank you for coming today.